Today, I am going to focus on something more deeper. Right? What I want to tell you is, by looking at the special cases, we can have a more deeper understanding to what we derive the wave impedance in general. Right? So if we divide the voltage phasor, total voltage phasor, by the total current phasor, this is what we have. So when we short circuit the transmission line, and I can walk back freely for a distance of L or D, imaginary, and it oscillates as a function of tangent beta L. So this is the moment where you have to think. Tangent. Beta is a constant, 2 pi divided by lambda, but L is a free parameter, right? So I can terminate my transmission line and walk for any length and look back and say that's my effective wave impedance. So L is a free variable. So now you have to think and look at this equation and tell me, what do you see? You have to come up with some kind of conclusive statements. That's a process where you are teaching yourselves, so you will remember forever. What I can see is, well, let's go back to the blackboard. The first thing I see is when I have short circuit, so I have purely imaginary impedance, right? And then it's a function of tangent beta L. So is there any limitation or boundary for tangent? Or let me write it in this way. Tangent beta L is smaller than what and greater than what? Tangent is unbounded. Right? Tangent oscillates from negative infinity to positive infinity. And then the entire thing is purely imaginary. What does it mean? It means when you short circuit a transmission line, the transmission line is lossless, okay? So that means the effective wave impedance will change its value as you change. So this is like I short circuit the transmission line and I walk for a certain distance, I look back. Oh, that effective impedance is purely imaginary, but its value can change from negative infinity all the way to positive infinity. Okay? But what's a physical meaning? What's a physical meaning when you have a purely imaginary impedance? Anyone wishing to answer? No? The TA wants to answer. If you have a purely imaginary impedance, it means effectively that short-circuited transmission line can function as an inductor or a capacitor. Right? This two wires is equivalent to an inductor or a capacitor, and it's variable, you are free to change it just by cutting the right length. Okay, so let's come back to this figure. So, if you short circuit the transmission line at the shorted position and you walk back for a certain distance within a quarter wavelength, it will be positive, right? Tangent is reaching infinity at pi over 2, 90 degrees. So that's 1/4 of wavelength. Within that distance, it will always be positive. And a positive imaginary number as an impedance means within this distance, that short-circuited transmission line is inductive. So you can fabricate an inductor of any value, 0 to infinity, just by using a segment of shorted transmission line. Okay? Now, once your distance passes lambda divided by 4 and 2, lambda divided by 2, then you have the negative cycle of tangent. And now you have a purely imaginary negative impedance. Negative impedance implies you have a capacitor. So this is the freedom of transmission line. So the reason why I derived all this wave impedance is really to show you that the transmission line itself, if you don't want to use it to deliver power, itself is very useful. If you don't have an inductor at hand, or you don't have a capacitor at hand, all you have to do is cut a piece of transmission line and just short it. Okay? And then you calculate the right length, it will function as a capacitor or an inductor. Right? So it's periodic. So it will be inductive, capacitive, inductive, capacitive. It's periodic. Look at the three figures very carefully and tell me, what do you observe? There is another comment. So you have to learn the right process of learning. The most efficient way to learn is you teach yourself. Okay? Not from my mouth. What do you see? If you're really good at math, look at sine beta d, cosine beta d. If you're not very good at math, I'm showing you the plots. Voltage, total voltage as a function of distance is having a periodicity of lambda. Right? Voltage, current, they are having a periodicity of lambda. But the wave impedance has a much shorter periodicity. Right? So this divided by this is giving you a periodicity of lambda divided by 2. So this means for wave impedance, whichever value you have at certain distance, it will repeat itself. You will have the same value by another separation of lambda divided by 2. For each lambda divided by 2 distance, you will recover the same value. Okay? So this is very useful for the later contents we are going to use today. But what does that mean? For students, if you want to earn points, now this is a trick all the professors like to do on your homework, on your examination. You don't have a quiz, bless you. It's periodic, right? So whenever we ask you a certain question, oh, what is the impedance value or the effective inductance here? If you want to write the full answer, you have to remember the answer is having infinite choices, right? It repeats after itself after lambda divided by 2. Okay? So that's the case for short-circuited. Next case for, I went through this already. You have a transmission line and you do nothing. Doing nothing is open. Alright? So the formal definition for open is your voltage is now having the maximum value it can be. But the current, when you have an open, you cannot have current. Right? So current has to be 0. So let's check. Just by changing gamma V to 1, positive 1, and your current total phasor takes on the form of sine beta d. So for d equals to 0, sine is 0. So indeed, yes. At the open end, you cannot have current, but your voltage is having the maximum. Again, remember, this is the fact due to that we're studying standing waves. Okay? So without showing you the last figure, can you guess? If I divide this one by this one, I have my wave impedance for the open case. What does it look like? Do you have to start everything over again? Or try to just slightly change the summary we derived on the blackboard? That's for short-circuited, but now it's opened. Is the resulting wave impedance unbounded or bounded? What is happening to its periodicity? So think about it. So all you have to do is divide this equation by this equation, and you have cotangent. It's still purely imaginary, but you have a negative sign, right? So you have a negative j, imaginary, negative cotangent. Cotangent is only the inverse of tangent. So basically, in this case, you have a piece of transmission line, you leave it opened. Effectively, your wave impedance as a function of distance is still purely imaginary. So you can also use this case to fabricate inductors or capacitors. But the fact you have a change in sign for your gamma V reflecting coefficient. So now, between the distance of 0 to lambda divided by 4, you have a purely capacitive reaction, and then it's inductive, capacitive, inductive. So the only change is from the short-circuited case, you have inductive, but now you have capacitive. Nothing else changes. Okay? The periodicity is still lambda divided by 2. Okay? Now, when you have a load, okay, you connect the load to the transmission line and you walk for a particular distance towards the generator and you look back. And that magical distance is lambda divided by 2. Okay? So let's use this equation. Okay? This is what we derived for the wave impedance. And now let's make L equals to lambda divided by 2. You still remember beta equals 2 pi divided by lambda. and now you make L equals lambda divided by 2. So tangent beta L is tangent pi. Right? Tangent pi. Tangent is sine divided by cosine. Sine pi is 0. So basically, in this case, you don't have to care about these two terms. Right? You don't care about these two terms. So your effective input impedance is Z0 multiplied by the normalized load. Normalized load is ZL divided by Z0. So basically they cancel. So what does that tell you? For whatever load you connect to the transmission line, whatever load, okay? And then you just walk for a distance of lambda divided by 2. You look back, including the transmission line and the load, at this particular magical distance, the wave impedance is equal to the load impedance. It's magical, right? So this is telling you, over a very long transmission line, you can say a lot of the length is invisible, right? When you choose the position right. So what happens when you are walking for an integer multiple of lambda divided by 2? It's the same, because tangent is a periodical function. So that means for the transmission line, no matter how long it is, and no matter what load impedance you connect to it, there are a lot of magical positions, discrete magical positions. Once you stand on the magical position, you look to the direction of the load. The transmission line plus the load gives you an equivalent wave impedance equals to the load. Okay, so I mean, in physics, in real life, this is like what I'm doing to you now. You're sitting at your home, maybe 1 kilometer away from me, but you can hear my voice, right? Although the camera is only 2 meters away from me, but you can hear my voice. So this is like engineers can cheat, right? Even though the load is 1,000 kilometers away from me, I can treat you as just 1 meter in front of me. When your magical position is determined, you can do that. You have the freedom to do it. Okay? You can effectively make the transmission line much shorter and do all the calculations there. Okay? So in your numerical calculations, even though you have 1,000 kilometers to be solved, you can make it short to be maybe 50 centimeters. Okay? So this is really calculation saving strategy once you know it. So this happens when your length is integer multiple of lambda divided by 2. So this is called the half wavelength line. Okay? Half the wavelength. Quarter wavelength. This is something deeper. Okay? So this is saying that I have a transmission line of certain characteristic impedance, and I have a load, and somehow I know that the load impedance is not equal to the characteristic impedance. But is there any possibility I have a second transmission line so that I can connect the second transmission line to my load, and I choose the right length so that together the second piece of transmission line and the load will match to the characteristic impedance of my first transmission line. Okay, again, we're using this formula. This is what I derived it for you today. So now the length is lambda divided by 4, and as we know, wave impedance is periodic with a periodicity of lambda divided by 2, right? So you will have a lot of answers. So once your length is lambda lambda divided by 4 and an integer multiple of half wavelength, all the results will be identical. So, tangent of this value, tangent pi over 2, that's, you have infinity. Right? So in this case, we can ignore this 2, the real parts, right? Because tangent is now super big. So we remove this 2. So in this case, the second transmission line with a length of quarter wavelength plus the load together will give you an impedance of the second characteristic impedance squared divided by the load impedance. So somehow I can say this value is equal to Z01, right? So this is one way to accomplish the so-called impedance matching, which will become our focus for the next class. But now I'm already offering you one way to accomplish, to match the load impedance to the characteristic impedance of the transmission line if you have a second set of transmission line with the right characteristic impedance. Okay? All you have to do is write down this is equal to Z01 and you find out the proper Z02. If you happen to have that set of transmission line, then you can perform impedance matching. Impedance matching means you have maximum amount of power delivered to the load because there's no reflection. Okay. So I talked about 5 special cases: short, open. They both give you purely imaginary impedance with unbounded value. So these 2 are especially useful for providing effective inductor or capacitors. Half wavelength is a magical distance where the load reappears at these locations. Quarter wavelength could provide you a potential way to accomplish impedance matching. Of course, in the end, our goal is to really have matched lines where we want to perform impedance matching so that we can eliminate reflection. So all the powers can be delivered. Okay? Once you don't have reflection, the maximum power can be delivered in the positive direction. Alright, so let's take a 10 minutes recess. So next class, for the entire next class, I'm only going to talk about one thing: impedance matching. A lot of mathematical derivations, so be ready.